Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi, Herman and Corin. So the existence of this podcast is made possible through the existence of serverless computing. Specifically, as we make clear on our website, we are using Modal, which is a serverless GPU platform. And basically, this podcast is produced using me sending in a voice prompt, that hitting a webhook, and that then driving a back-end pipeline. And as I mentioned previously, that pipeline has taken quite a bit of time to develop. And finally, we have something that kind of resembles a good and reliable way to create these, I think, interesting episodes. And I was thinking earlier, if I was to describe how serverless works to someone, I could do a pretty decent job, I think, at describing it from the consumer perspective. In other words, that instead of renting out a GPU, which I've looked at before and looked at that option, really expensive, because GPUs are incredibly energy. They require a lot of energy, and the type of GPU that's required to develop, to even produce a single episode of something like this, I can't remember off the top of my head which GPU that we're using. I think we've tried a few of them, but I looked at the cost a couple of times just out of interest. How much would it cost to actually buy that GPU? And tens of thousands of dollars. So these are enterprise grade data center GPUs. They're not something that, unless you have a vast fortune and you have a lot of patience and a great cooling system, that you're going to be buying off the internet and installing in your apartment. It's not really viable for almost anyone, I would say. So serverless provides a great solution in these cases, where I don't need this podcast pipeline running 24/7. I just need that when I send in a prompt, it sends it off to the pipeline. And the GPU, my job is running on the GPU as a container for a certain number of seconds. We're paying per second, and after much trial and error, I found out that this was actually cheaper than using APIs, and I've come to really like the process, because there's almost kind of a mystery in APIs where you don't know exactly how it works under the hood. And something I like about the serverless GPU model is it's very pure. You can see, okay, I'm starting up a container on this machine. Here are the logs. It's done. This is how much I paid. So even if it's the same amount, I've come to quite like serverless, even though you won't have to go far in the internet to find horror stories of people who ended up with gigantic builds on serverless. But so far, it's actually been the most cost-effective way of making these episodes to date. So I can explain the operation from a consumer perspective, but I always wonder, who are these serverless providers? For some reason, the metaphor that jumps to my mind is, if one of those sushi restaurants where they have the sushi revolving around on a conveyor belt, and it's an all-you-can-eat style thing, and the diners grab at something. For some reason, that's the analogy that sort of comes to my mind when I think of how it must work from the provider perspective. You've got a lot of customers. They're running these jobs, these functions that are containers, but the containers might be persistent in the sense that the configurations maintain, but they're ephemeral. They kind of hop on to the infrastructure for a few seconds, they hop back off, they go idle, they hop on, they hop off. And my only question is really, well, who are these providers, people like Modal, and how do they actually make that work? Because they're in the business of making money like everyone else in business, and they have large customer bases, and they can't necessarily predict when each customer is going to be running, what the cumulative demand is going to be. So my question is, are these sitting between the ultimate physical providers of the infrastructure, the giants like AWS and Google, etc., and kind of offering a service on top of them? or do they actually own their infrastructure? And how do they, do they have basically elastic underlying infrastructure such that it doesn't really matter to them how many customers are looking to run a function at a given time on, a certain in-demand GPU, or do they have to throttle demand accordingly based on the underlying infrastructure they have access to? Herman and Courtney, I'd love to get an understanding of how the actual provision of serverless infrastructure works from those who offer it, like Modal, and provide a great service that me and I'm sure many other customers really appreciate. But I'd love to understand how it actually works under the hood.
Hey everyone, welcome back to My Weird Prompts. We are coming to you from our usual spot here in Jerusalem. It is a bit of a rainy February morning here, the kind of day where the stone walls of the old city look almost silver, and we are huddled in the kitchen with way too much coffee. Today we are pulling back the curtain on something that actually makes this very show possible, and it is a topic that has been sitting in our inbox for a while.
Herman Poppleberry here, and I am particularly excited about this one because it gets into the real plumbing of the internet. Our housemate Daniel, who is usually the one finding these bizarre prompts for us, sent us a voice note earlier today asking about the literal hardware and software that runs our backend. He wanted to know about the serverless graphics processing unit providers like Modal. Specifically, he asked if they are just middlemen sitting on top of Amazon or if they are building their own digital fortresses.
It is a great question because, as Daniel mentioned, we use Modal to run the entire pipeline for this podcast. When he sends in a voice memo, it triggers a sequence of events that would have been impossible for a small team 5 years ago. We are talking about transcribing audio with Whisper, processing it with the latest large language models, and then synthesizing voices, all happening on these high-powered chips that we do not own and could never afford to keep in our apartment.
Oh, absolutely not. If we tried to run a single Blackwell B200 in this kitchen, we would blow every fuse in the building and probably melt the floor tiles. Daniel was hitting on a really interesting tension in his prompt. On one hand, you have the massive cloud giants like Amazon Web Services and Google Cloud Platform, and on the other, you have these specialized, developer-focused platforms that feel much more agile. He wanted to know how they actually manage that elasticity without just being a thin wrapper around a more expensive service.
Yeah, and the economics of it in early 2026 are just wild. If you look at the price of an NVIDIA B200 today, you are looking at $40,000 to $50,000 for a single card. That is for the chip itself. That does not include the server rack, the specialized power delivery, or the cooling requirements. For a small startup or a couple of guys in Jerusalem, buying that hardware is a non-starter.
It really is. And it is not just the hardware cost, it is the expertise. These data center grade chips are not like the ones in a gaming laptop. A single B200 can draw up to 1,200 watts of power. That is almost double what the previous generation, the H100, required. So, let us dig into Daniel's first question. Where does the hardware actually live?
From what I have gathered looking into the architecture of companies like Modal, Replicate, and Core Weave, the answer has shifted significantly over the last 2 years. In the early days, say 2023, a lot of serverless companies were essentially reselling instances from Amazon or Google. They would wrap a nice user interface around a standard cloud virtual machine and charge a premium for the convenience.
But that model had a major flaw, which was the margin. If you are paying Amazon's retail prices for a graphics processing unit, which can be as high as $14 an hour for a Blackwell instance, and then trying to sell it in smaller slices to developers, you are basically subsidizing your customers until you go out of business. Plus, the big cloud providers are notorious for having limited availability of the newest chips. They keep the best stuff for their own internal projects first.
Exactly. So what we've seen is the rise of the Tier 2 clouds. Companies like Lambda Labs or Core Weave have built their own massive data centers, specifically optimized for artificial intelligence workloads. Core Weave, in particular, has been fascinating to watch. They raised over $1 billion in their Series C recently just to build out more capacity. They do not try to offer every service under the sun like Amazon does. They just offer massive amounts of compute. A provider like Modal often partners with these Tier 2 giants to get bare metal access to the hardware.
That is a crucial distinction. Bare metal means they are not running on top of another company's virtualization layer. They are talking directly to the silicon. This is how they managed to get those lightning-fast boot times that Daniel was talking about. If you were sitting on top of a standard Amazon instance, you would have to wait for their operating system to boot, then your container to start, and by then the user has already refreshed the page. Modal has built their own custom, AI-native runtime that they claim is 100 times faster than standard Docker.
I was reading their technical blog recently, and they mentioned that they use a specialized version of the Linux kernel to handle this. But let us talk about the orchestration, because that was the second part of Daniel's question. How do they handle the elasticity? Because at any given second, they might have 10,000 developers hitting their endpoints, and then 10 seconds later, it might be only 100. How do you keep those chips busy without wasting money?
This is where the engineering gets really impressive. The secret sauce is something called bin packing and cold start optimization. Imagine a giant warehouse full of graphics processing units. Each of those chips has a finite amount of memory, or VRAM. For a B200, that is 192 gigabytes. The orchestrator has to be like a grandmaster of Tetris, but the game is played in milliseconds.
So the orchestrator is looking at the incoming requests and deciding which physical machine has enough free memory to handle that specific task.
Exactly. But it is even more complex than that. They are often using micro-virtual machines. We have talked about the Firecracker technology that Amazon open-sourced a few years ago. It allows you to launch a virtual machine in a fraction of a second. But for graphics processing units, it was historically very difficult because you had to pass the hardware through to the container. The container needs to think it has direct access to that NVIDIA chip, and until recently, Firecracker did not support that very well.
I remember seeing a GitHub issue about that. It looks like they finally cracked the PCIe pass-through for micro-virtual machines in late 2024 and early 2025. That was a huge breakthrough for the industry.
It was the missing link. Now, a provider like Modal can spin up a secure, isolated environment with full access to a graphics processing unit in less than a second. But even with fast boot times, you still have the problem of the model itself. If you are running a massive model like Llama 3 or Mistral, you have to load gigabytes of data into the chip's memory before you can even start processing. That is the real bottleneck.
Right. And that leads to what they call the cold start problem. If the model is not already sitting in the memory of a chip, the first user has to wait for it to load. I saw that Modal recently launched something they call Graphics Processing Unit, Memory Snapshotting. Have you looked into that?
It is a game changer. Instead of loading the model from scratch every time, they basically take a snapshot of the chip's memory state after the model is loaded. When a new request comes in, they can restore that snapshot almost instantly. They have shown that for some models, it can reduce the cold start time from 2 minutes down to just 10 or 12 seconds. It is like being able to pause a video game and then resume it on a different console instantly.
That is incredible. It basically makes the distinction between a warm and a cold container much smaller. But let us talk about the demand side for a second. How do they ensure they do not just run out of chips? Because if a major client suddenly decides to scale up to 10,000 concurrent functions, that could theoretically wipe out the available supply for everyone else.
This is where the multi-cloud strategy comes in. While they have their primary partners like Core Weave, they also have the ability to spill over into other providers if they hit a capacity limit. They use a global scheduler that looks at the availability across multiple data centers. If Virginia is full, your request might get routed to a data center in Oregon or even Europe, depending on the latency requirements.
And they use pricing as a throttle, right? I noticed that the price for a B200 on Modal is around $6.25 per hour, which is actually very competitive compared to the on-demand prices at the big clouds.
It is, and that is because of the utilization. If you rent a graphics processing unit for a month, it might cost you $3,000. But if you only use it for 10 minutes a day to process a few podcast episodes, you are wasting 99% of what you paid for. The serverless providers can sell those same minutes to 1,000 different Daniels. They are arbitraging the idle time of these chips. It is the ultimate sharing economy for silicon.
I also think about the transparency that Daniel mentioned. He likes being able to see the logs in real time. When he runs a command on his laptop here in Jerusalem, and it executes on a chip 3,000 miles away, it feels like it is running locally. How do they handle that streaming data without it feeling laggy?
That is mostly clever networking. They use specialized protocols like gRPC and high-speed backbones to tunnel the standard output of the container back to the local terminal. They are also using edge locations for the initial handshake. So your request hits a server near you, which then tunnels it through a high-speed line to the actual compute cluster. It is a very layered cake of technology.
Let us talk about the hardware limitations again. We touched on this back in episode 25, but it seems even more relevant now. The VRAM is still the biggest constraint, right? If you run out of memory on a graphics processing unit, the whole process just crashes. You cannot just swap to the disk like you can with a standard processor.
Exactly. And that is why these providers have to be so precise with their bin packing. If they put two tasks on the same chip and they both try to use 80% of the memory at the same time, the whole machine goes down. So they use custom drivers and specialized container runtimes that can monitor the memory usage in real time and move tasks around if things get too crowded. It is a constant balancing act.
It is funny that Daniel mentioned the mystery of API providers versus the purity of serverless. I think he is onto something there. When you use an API like OpenAI, you have zero visibility into what is happening. You send a request, you wait, and you get a response. You do not know if they are running on an A100, an H100, or a cluster of older chips. You also do not know why it is slow. Is it the model? Is it the network? Is it their database?
With the serverless container model, you are in control of the code. You can see exactly where the bottleneck is. If your image processing takes 5 seconds, you can look at the logs and see that 4 seconds were spent just downloading the weights of the model from a storage bucket. That transparency is why developers love it. It takes the magic out of it and replaces it with engineering.
That is a great point. The data transfer problem is often overlooked. These models are huge. A standard stable diffusion model might be 5 gigabytes, but some of the newer multimodal models are 50 or even 100 gigabytes. If you have to pull that much data from a hard drive to the graphics processing unit memory every time someone makes a request, it is never going to be fast.
Right, so the providers build these massive high-speed internal networks. They use NVMe drives on the host machines to cache the most popular models. So when you say, I want to run this specific model, the orchestrator tries to send your job to a machine that already has those files sitting in its local cache. They are essentially building a globally distributed file system just for model weights.
I also want to go back to the physical infrastructure for a second. Daniel asked if they own it. While many start by renting, as they scale, they almost always move toward owning, or at least co-locating their own hardware. Because when you own the hardware, you can modify the BIOS, you can optimize the power delivery, and you can choose exactly which networking cards to use. If you can squeeze 5% more efficiency out of a rack of servers, that is pure profit at scale.
And that is where we get into the liquid cooling. I have seen some of these newer data centers using liquid immersion cooling where they literally dunk the entire server into a non-conductive fluid to keep it cool. It sounds like science fiction, but it is becoming necessary. A rack of Blackwell chips can generate so much heat that traditional air cooling just cannot keep up. You would need a hurricane of air to move that much thermal energy.
That is wild. It makes Daniel's point about the cooling system in his apartment even more relevant. Even if he could afford the $50,000 chip, he could not keep it cool without his electricity bill doubling and his room feeling like a sauna. By moving that problem to a serverless provider, he is essentially outsourcing the thermodynamics of the project.
He really is. And it allows for these weird experimental workflows, like what we are doing here. We do not need a supercomputer all the time. We just need a supercomputer for 3 minutes at 4 o'clock on a Tuesday. It democratizes the brains of the internet. We have seen people building everything from medical imaging tools to automated video editors on these platforms. Things that would have required a whole team of infrastructure engineers 5 years ago are now being built by solo developers in their bedrooms.
It also changes how you think about architecture. Instead of building one big monolithic application, you build a series of small, ephemeral functions. It is much more resilient. If one part of your pipeline fails, it does not take down the whole system, and you only pay for what you use. We can run this entire show's back end for less than the cost of a couple of cups of coffee in Jerusalem.
It is a good time to be a builder, that is for sure. And I think Daniel's curiosity about the mystery of it is something a lot of people feel. We are so used to technology being a black box. But the serverless model, at least the way companies like Modal do it, is surprisingly transparent if you know where to look. It feels more like a collaborative tool than a service you are just consuming. You feel like you are working directly with the hardware, even if that hardware is in a different time zone.
So, what do you think the future looks like for these providers? Do they eventually get swallowed up by the big three cloud giants, or do they become the new giants themselves?
I think we are going to see a split. Some will definitely be acquired because Amazon and Google want that developer experience. They want the cool factor and the ease of use. But I also think there is room for a few of these specialized providers to become massive independent companies, because the needs of artificial intelligence are so different from the needs of a standard web server. A web server needs high availability and low latency for small packets of data. An artificial intelligence workload needs massive bandwidth, huge memory, and long-running compute cycles. They are fundamentally different engineering problems.
Exactly. It is like the difference between a city bus and a heavy-duty freight train. They both move things, but you would not use a bus to move 10,000 tons of coal. Well, I hope that sheds some light on the mystery for Daniel and for everyone else listening. It is a fascinating world under the hood.
It really is. And if you are out there building something with these tools, we would love to hear about it. The way people are stitching these different services together is where the real innovation is happening right now. It is not just about the models. It is about the plumbing.
Absolutely. And hey, if you've been enjoying these deep dives into the weird world of prompts and the tech that powers them, we would really appreciate it if you could leave us a review on Spotify or whatever podcast app you use. It genuinely helps more people find the show. We are trying to grow this thing, and every review counts.
Yeah, it really does make a difference for a show like ours. We love doing this, and the more people we can bring into the conversation, the better. You can find all our past episodes, including the ones we mentioned today about graphics processing units and artificial intelligence inference, at our website, myweirdprompts.com.
There is a contact form there too, if you want to send us your own weird prompts. Or just come find us in Jerusalem. We are the ones arguing about container orchestration over a plate of hummus at the market.
Speak for yourself, Herman. I am usually the one just trying to get the code to run while you explain the difference between a hypervisor and a micro-virtual machine.
Fair enough. Well, this has been another episode of My Weird Prompts. Thanks to Daniel for the prompt, and thanks to all of you for listening. We will see you next time.
Catch you later. Stay curious.
And keep those prompts coming. Bye for now.
Wait, Corn. Before you stop the recording, I just thought of something. If we did get that liquid cooling set up, we could probably use the waste heat to keep the hummus warm.
Herman, no. We are not dunking servers in the kitchen. The landlord already thinks we are running a crypto mine because of the fan noise. Seriously though, thanks for listening everyone. We will be back next week with another one. We might even talk about the specific trade-offs of scaling text-to-speech workloads, which connects perfectly to what Daniel was asking today.
Oh, that is a good one. We can look at episode 346 for that. All right, now I am actually hungry. Let's go get some lunch.
Lead the way, Herman Puppleberry. I think it is your turn to pay.
Was it? I thought we were arbitraging the lunch bill today.
Nice try, Herman. Nice try.
Worth a shot. Goodbye, everyone.
Goodbye.
This has been My Weird Prompts.
A production of two brothers and a very busy housemate.
Indeed.
Okay, now I'm really stopping the recording. Done.
Wait, is it still on?
No, I am. Wait, now it is. Just kidding. Bye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.